So I'm going to start this talk off by giving two apologies. The first of which is because I have injured myself last week and I'm still recovering a little bit, so if halfway through the talk I make a very strained face and start moving very slowly, it's because I hurt myself again. And the second apology will be because I'm a postdoc. I just got my PhD last year, and I've spent about 5 years giving talks to one of two groups. Either I'm talking to a bunch of professors and fellow researchers of mathematics, and I can usually say things like, oh, you apply the Weil criterion and then do some other stuff, and everyone knows immediately what I'm talking about. Or else I'm talking to a bunch of smug college freshmen, like this gentleman over here, and I have to browbeat them over the head that when you're, for example, looking for absolute maxes and mins, you must test the endpoints. So, in other words, I haven't hit this point yet where I know how to talk to a group of students who are above the level of doing calculus, they're interested in mathematics, but aren't yet at the point where I can just list off theorems and you go, oh yeah, of course. So, if ever I start drifting into one of those categories, feel free to raise your hand and say, Dr. Vandehey, what does that mean? I am perfectly okay with that, and well, here it goes. So, I'm going to talk about normal numbers. And unfortunately, this is perhaps one of the most overused words in mathematics. I went on Wikipedia just to see how many different definitions of normal there are. So there are normal vectors, normal lines, normal matrices, normal subgroups, normal distributions, and so on and so forth. And it went through 24 different uses of the word normal. We're going to be talking about this, normal numbers. So what does it mean for x to be normal? So you have a number x with a base 10 expansion. All right, classic decimal expansion, and maybe we could write this as 0.A1, A2, A3, A4, A5, and so on and so forth, because I don't care about any integer parts over here. I just care about everything after the decimal. And what does it mean to be normal? Well, if I pick a string of k digits, say I pick a very simple string, 4. String of digits, it's only one digit long. Then this should appear in the expansion with the same frequency as any other string of k digits. So I said 4, well then I should also mean, well, okay, here's some other strings, 5, 6, 9, 1, and so on and so forth. I want 4 to appear as often as 5, as often as 6, as often as 9, as often as 1. And I want this to be true even if I pick a longer string of digits. So say 31692 appears as often as 0, 0, 0, 0, 0. So it's a fairly basic idea. I just want things to appear with the same frequency as everything else, that they should appear with the same frequency as. Okay, so that's kind of the really basic definition. What about making this precise for mathematician's sake? Let S be a string of k digits. Let this crazy notation denote the number of times the string appears in the first n digits. Okay then, well, x is normal if and only if for all strings S, we have that the limit as n goes to infinity of this weird counting thing over n is equal to 1 over 10 k. So, going back to this example here, this says that the number of times I see 4 in the first n digits should approach 1/10 of the time as n gets big. And the number of times I should see 31692 in the first n digits should approach 1 over 10 to the 5th as I have more and more and more digits. Well, okay, it's really easy to talk about things that aren't normal. That turns out to be a much easier question to deal with. Well, I can give a really silly example of this, 1/2. Well, why is that not normal? So you're never going to see a 1, ever, let alone see it 1/10 of the time. And you can even extend this argument out quite a ways and say that, well, you pick any rational number and it's eventually periodic. So after some point, you're never going to see certain strings that are rather long. So I mean, here's another one. 0.2382526. 26, 26, 26, 26, 26. Well, you kind of notice that basically everything that happens really kind of happens here. And after this point, it starts getting really boring. And you could really easily pick a string which never occurs. 7 never occurs. 266 never occurs. And so basically, anything that's rational is not normal. But that's kind of a cop-out. It's way too easy. It is possible, for example, to give you an example of a normal number, or I'm sorry, a non-normal number, where everything appears at least once. Yes, that is 10 to the n factorial. So what does this look like? 0.1, 2, 0, 0, 0, 3. Well, you can kind of guess pretty quickly that 0 is appearing more than anything else. And even though every possible string will occur at least once, namely, pick your favorite string, let it be n, it'll appear sometime. And, well, okay, it appears, but 0 dominates everything. This is clearly not normal. Okay, but if I make it sound like normal numbers are kind of a rare thing, this is actually the opposite of the truth. As it turns out, practically everything is normal. If you were to pick a number at normal right now, you would almost certainly, with probability 1, be picking a normal number.
You mean at random?
At random, yes. At random. That's a very important thing there. And this is a little counterintuitive if you haven't seen, for example, probability theory yet, which I presume most of you probably haven't. Because if I ask you to pick a number at random, odds are you're going to pick either A, a rational number, B, an algebraic number, or one of people's kind of favorite transcendental numbers like pi, e, or natural logarithm of 2, or some combination of these. And that's not really that random. That's a very select set that you're picking things from. And, okay, how do we actually talk about choosing something at random? Well, now I'm going to roll a d20 to make a nerdy joke, and talk about d10. So for those of you who haven't played Dungeons & Dragons, this is a 10-sided die, commonly known as a d10, and presuming that everything has gone right in the manufacturing, it has an equal chance of arriving at any number from 0 to 9. So if I want to pick a number at random, there's a very good procedure for doing this. Namely, I start at 0.6. And then 0. And then 6. Then 6 again. Now, presuming that my die hasn't been messed with by the GM, we will assume that it's going to actually come up with every number between 1 and 10, all with equal probability, and we're going to guess that when we do a procedure like this, and you pick each one of these at random between 0 and 9, that we should get a real number at random. Of course, there's one little tiny thing we have to worry about, which is the 9s repeating versus 0 repeating, but as it turns out, that's such a rarity it practically never comes up. So if we pick a number at random this way, then you start to get the idea that yes, most everything should be normal. Well, why? Because if I start with, say, a 1-digit string, that's just asking, well, what are the odds when I toss this that it's going to come up with a particular digit? When I ask, okay, what about a 5-digit string, that's just asking, what's the odds that I'm going to get a particular combination when I roll this 5 times? And you expect, well, it's going to be random, that I'm going to see any particular combination the same as any other particular combination of the same length. So we expect that, probability 1, when I do this procedure, I'm going to get something that's normal. So almost all real numbers are normal. That's kind of the neat part about it. And as you might guess, there's nothing particularly special about base 10 here. I could flip a coin and use that to determine a base 2 number, and almost certainly that's going to be base 2 normal, as opposed to base 10 normal like this one. And I could do it with a 6-sided die, with a 20-sided die, with a 12-sided die, so on and so forth, and we can just keep doing this procedure. And in fact, so for any base B, almost all real numbers are normal to that base. But then this has a very interesting corollary. If you do this procedure and you pick a number at random, not only is it likely to be normal to whatever base you picked, it's likely to be normal to every possible integer base. Base 2, base 3, base 4, base 5, base 6, base 7, base 8, base 9, all of them all at the same time. Okay, so at this point it seems like normal numbers are a pretty awesome thing. They're neat, they have cool properties, they're everywhere. And then someone asks the question. And the question, as it usually goes in mathematics, is, okay, you have a neat property about real numbers. What about pi? What about pi? So a lot of this stuff talking about real numbers, this actually happened at the end of the 19th century, around 1898, and this was a famous name, this was Borel. And then, of course, someone asked, well, is pi normal? Well, I can only give you so many digits of this because I'm not one of the people who memorizes a whole bunch of them. Okay, 3.14159, blah, blah, blah. I'm assuming there's someone in the room who knows more digits. Some people are smiling, so I'm guessing yes. Okay. Well, what do we know? Well, a priori, we don't really know that much. And in fact, when we were starting to build computers and using them to solve math problems, one of the first things we did with them was say, well, hey, we have this computing power. Why don't we use it to compute a whole bunch of digits of pi and see if they look like they're a normal distribution? That was one of the first reasons why we started doing this. In fact, let me toss out another famous name. John von Neumann said, hey, why don't we calculate pi on the ENIAC? And they were able to get about, I think, 2,000 digits out of this. And we're able to say, hey, it looks like it's being fairly normal. And in fact, some more recent calculations have asked this same question. What if you ask about a trillion hexadecimal digits? That's base 16 pi. Because we can calculate this really fast these days. And, well, what's the distribution of, say, the one-digit strings? Well, the worst one is the digit D, which is basically 13, because we're in base 16. And it appears 62499613666 times. And if everything were appearing with the same frequency, we would expect it to appear 62500000000 times. So as you can see, it looks like it's not doing too bad. This is the worst one of the one-digit strings. Everything else is even closer to this time. So it appears from the calculations that so far pi acts fairly randomly. It acts like it's a normal number. But do we know? No, we don't. We, in fact, know almost nothing. E, natural logarithm of 2, square root of pi, pick any other irrational number that you like that isn't obviously not normal, like the one I showed you before, and we don't know if it's normal at all. We have almost none of these that we know anything about. And this is the point where I have to, browbeat my own profession a little bit. Remember, this came up in, the end of the 1800s, start of the 1900s. It's been over a century since we asked this problem. We're not really any closer to answering it. And of course, that's with the big problem of, okay, how do you talk about mathematical progress? How do you talk about how close you are to solving a problem? But really, we haven't had any breakthroughs, any major insights that come really close to being able to solve is pi normal. Well, okay.
Do we know of any normal numbers?
Yes, we do. And in fact, that's what I'm going to talk about now. So, what can we do? Well, if you just give me a number and ask me, is it normal? My answer will probably be, I have no idea. However, if you just ask, can you give me a normal number? My answer to that is, sure. In fact, we have lots of examples of those. And the most classic one was due to, D.H. Champernowne, who was at the time an undergraduate at Cambridge, and this was his construction of a normal number. It's a very simple pattern. Just take all of the integers and concatenate them one after the other. And you saw a very nice example of this on the poster, which went all the way up to 500. And yes, this is actually a normal number. Every time I look at this, I keep going back and forth on whether or not I believe it, even though I have seen the proof. In fact, I've seen the proof so many times I could probably give it from memory at this point. But yes, it is actually normal. And okay, so this is the way I typically go about looking at this number and battling with myself about whether or not it's normal or not. First thing is that, well, obviously it looks like everything appears and everything appears in roughly the same frequency, so okay, yeah, should be normal. And then I get to thinking about it and I go, okay, well, way out here in the decimal expansion, I'm going to hit the part where we're at 999999999, let's say about 100 nines, followed by 1000 with 100 zeros. And then for a whole long time after this, there's 96 zeros, that for a whole long time, I'm seeing way too many zeros in all of these numbers. And it just seems, well, okay, that doesn't seem right.
But then you're going to have a later stretch where you'll have just a whole bunch of ones for over and over until the next one.
Yeah, so again, this seems really kind of weird, and this is why I battle it out with myself of, okay, just a priori, do I believe that Champernowne's constant is normal? And ultimately the answer comes down to yes, it is, and the question is why? Well, it comes back to this. So when I talked about choosing a number at random, and I said, okay, I'm basically tossing a d10 an infinite number of times, and you expect that when I do this, because of laws of averages, that any particular combination of digits should appear the same as any other combination of digits. That's just what we expect from long-term averages. Well, if we're talking about long-term averages, we don't have to talk about infinite averages. We can talk about, well, what if we just pick a really long set of numbers? So if I'm looking for a particular combination, like let's say I'm looking for the digit 4, and I roll my dice hundreds and hundreds and hundreds of times, I expect the number 4 to appear with roughly the right frequency most of the time. And we can put a value on it. So what that's saying is basically, okay, pick a string, S of k digits, look at all integers n with L, L digits with L much bigger than k. Well then, I would expect that in almost every one of these, I'm going to see this string appear with roughly the right frequency, because, laws of averages. And we can actually put a value on it. We can say roughly how many of these are going to have this appear to roughly the right value. So the technical term for this is we say n is epsilon k normal if every string of length k appears to within epsilon of the right frequency. And then the way that the proofs usually go is to say, well, if you fix epsilon and k, and you ask, okay, how many n are epsilon k normal? Like, let's say, how many n up to x are epsilon k normal? Well, it turns out the answer is n to the 1 minus delta, where delta is potentially small, based on epsilon and k. But notice that this is much, much, much smaller than this once n gets really, really big. Well, this allows you to prove lots of other neat things. So instead of picking, as Champernowne did, he picked every integer. Because if he picks every integer, then surely he's going to get so many that the set of numbers that have bad properties, oopsies, I said this the wrong way. The set of numbers that are bad, that have the wrong properties, are very, very small. So if you just pick a set that has, you pick a set of integers that's sufficiently dense in the set of all integers, namely that it's going to be eventually larger than this for any n big enough, then you're going to get a normal number as a result when you concatenate all those values together. And this leads to perhaps my favorite number of all time, and one of my favorite proofs of all time, because, as it turns out, the primes are sufficiently dense. Which for anyone who's taken basic number theory, whenever you think of primes, that's usually your set of example of not dense. That's really sparse. They're very infrequent. But as it turns out, they're dense enough to satisfy that condition. And so this number here turns out to be normal. Because, again, you're just hitting so many numbers, and most of them are going to be epsilon k normal. And that turns out to be enough to do it. Okay. So this is kind of one big set of things that we've been able to do. I have worked on some of these problems. In fact, I just had a paper come out recently with Paul Pollack, for those of you who know him here at the department. And we've talked about, well, okay, what if we ask for other sets of numbers besides just all the integers or all the primes? Well, you can do other fun, crazy sets there. Let's see, for example, you could do where sigma is the sum of prime divisor, or I'm sorry, sum of divisors function. So, for example, sigma of 4 is 1 plus 2 plus 4, or 7. As it turns out, you get the same thing happening here. So this is kind of one large set of normal numbers that we can construct. There are other examples, because maybe you don't like that kind. So I typically tend to call these, for example, combinatorial approaches because they all work on this idea of, well, you're just counting things. Right? You're counting the likelihood that you're going to hit a certain good property, and then it just, okay, so long as you count things right, everything should work out. And then there's another method, which, for whatever reason, I'll call the trigonometric method. And this allows you to prove things like this. Why am I doing this wrong?
You have a good memory.
So this is all of the squares concatenated one after the other. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, so on and so forth. This turns out to be normal as well. And the method of proof is a little bit different here, because unfortunately, the set of squares is not a very dense set at all. So you have to rely on another idea. And part of the idea here is just that, well, again, almost all numbers satisfy this property of being epsilon k normal. So we would expect that unless for some reason you're obviously designed not to hit those numbers, if you just have a random function, odds are it's going to hit epsilon k normal numbers most of the time, just because there's so many of them. And as it turns out, you can find ways of proving that, for example, x squared does this. And the usual method by which this works is you find a way of switching from this to what are called trigonometric sums. And without saying too much more about these, it's somewhat along the idea of wanting to show that something like this is very small, where p over q is just some rational number. Okay, so that's another method.
Can you generalize that to like cubes or anything higher, or is it pretty limited?
Yes, in fact, there was a result. This is by, of course, since we're talking about number theory here, Erdős comes up. And this is Erdős and Davenport showed that you can actually stick any integer valued polynomial you like in here, and it will work.
Wow.
And again, that's just because if you pick a sum of this type, where instead of n squared you have a polynomial here, we know more about those. So we can have a good bound here, which tells us about good things here. And so again, plugging some of my own research here because I'm the one who's speaking and I'm allowed to do that. So one of the things that Paul and I have most recently done is we've actually shown that this particular case here of looking at n squared can actually fit into this case over here if you study it in just the right way. And you can, instead of trying to look at crazy sums like this, you can just do a counting argument. And then another thing that I happened to show at one point was a proof of this method, which gives a number that you would really, really not think is normal. And to do this, I need to do a quick explanation. A little omega function. It's a very fun function. Little omega counts the number of distinct prime divisors of n. So little omega of 12 is just 2, because it only has 2 distinct prime divisors, 2, 3. And, okay, so there's that. And let omega 1/2 of n denote the last half of the digits of omega n.
Ordered from smallest to greatest?
Looking at the, no, just as they are. So if, say, omega of n is equal to 1, 1, 2, 3, 1, 9, then omega 1/2 of n would just be 3, 1, 9.
Okay.
And if, there's an odd number of digits, pick one extra. Well, as it turns out, this number is normal. Wacky thing. Especially because you don't even see the number 9 until after 200 million digits have gone by.
Great.
Because that's how long it takes to find a number that has 9 distinct prime divisors, 2 times 3 times 5 times 7 times so on and so forth. So, yeah, kind of wacky. And as it turns out, omega of 1/2 is normal. If you use omega by itself, it turns out it doesn't work, for reasons that are probably a little bit too technical to get into right now. Okay, so there was the combinatorial method of counting things that gave us Champernowne's constant and the Copeland-Erdős constant, which was the primes altogether. There's this other crazy method which gave us, okay, you concatenate all the values of, say, squares or polynomials, or this crazy thing that someone thought was a good idea to look at. There is basically one other thing we can do. And I don't really know a good name for it, so I just call it the rational method.
Is that 10 to the c to the n?
That is 10 to the c to the n. So I think this is either the Korobov numbers or the Stoneham numbers, and I forget which, because unfortunately I forgot to write it down. It's one of them. I'll give credit to both of them. And these are kind of wacky things as well. It's a lot less obvious to see why does this appear to be normal than it was for some of the other cases where you'd say, well, pick a string, it's almost likely to be normal. Well, okay, so what's kind of the idea here? Well, if you chop it off after a certain point, then this is rational. And if it's rational, therefore, it's going to be periodic. And if it's periodic, then it has a string which makes up a period. And kind of by the same argument as last time, if you just, somehow picked a random string as your period, well, almost certainly you would expect this to have good normality properties. So with luck, when you do this, you would expect most of the time that you truncate it off, you're going to see a string that's getting better and better as you go farther and farther out with the n. So for example, with this one, if you actually look and see, okay, what are the various strings it's going to be composed to look like? Well, first off, you get 0 for a while, then you get 3 as a period for a while. So the actual number looks something like 0.000333. Then you get 4 for a while. Then you get 814 for a while. Then you get 604938271 for a while. And you keep on going farther and farther out, keep on getting longer and longer periods, and you keep hoping that, well, if you did things right, maybe these periods have good normality properties. And as it turns out, all you need for it to be true is that this is co-prime to 10. Oh, this is the particular example where C is 3. Okay? That's about all we know. That's as good as we've done.
So do you know that every normal number has to be transcendental?
No.
You don't. So
We
it
don't.
could be just irrational.
Yeah, all we know about it is it has to be irrational. There are, for example, transcendental numbers that are not normal. For example, the number I stuck up over here near the start of the talk, which had all of these strings but way too many zeros, is transcendental, but clearly not normal. But outside of that, we don't know. And I should add here that I've known about normal numbers since I was in high school, and did the crazy Wikipedia searches or whatever it was I did back in the day, and found this strange thing called normal numbers. And this is the part that has fascinated me through high school, undergrad, graduate, and now still as a postdoc, which is we're talking about randomness. Normality is about randomness. And yet all the examples I can give you of a normal number don't look random at all, right? I mean, look at Chambernoun's constant. That does not look like something that's random. What's the deal? What's going on here? And, of course, various people will give various different answers for this, but the answer I'll give you is that the notion of randomness is really kind of a cop-out. It's a silly word that we use in English that doesn't have the same meaning when we talk about it in mathematics. And the reason we care about numbers like pi or e or the square root of 2 isn't because they're random. It's because they do have patterns and they do have structure and they do have these properties that we like. So even though we look at, say, the base 10 digits of pi and we say, well, that looks pretty random, we can certainly make pi look very non-random. So since I'm in a room full of people who like their mathematics, I'm presuming most of you have seen this. Perfectly good way of making pi look very non-random. Well, okay, but you'll notice this doesn't look like anything we've looked at so far today. But there is something that does.
Is this like something by Ramanujan?
That is not by Ramanujan, no. This was originally discovered by Simon Plouffe and has been known as the Pdp algorithm for, let's see if I get this right, Borwein, Bailey, and Plouffe together, who published the paper that first talked about it and found you can do this for a whole bunch of other different kinds of constants as well. There's these wacky formulas. But what you should see is that, well, if I look at this, I look at that, and that's much closer. These look a lot more similar than, say, that and anything else we've seen today. And in fact, this is about the closest we've come to being able to talk about normality in Pop, is to say, well, we know how to prove the normality of things that look like this, and we'd like to know the normality of things that look like this. We've taken something that we hope has these random properties, and we try and structure it in a particular way that we can talk about it in terms of things we already know how to do. So what we're really hoping for is to find a way to go from this to that. And noticeably, the thing that's really kind of bugging us right now in the mathematical community is that. So every time I add on a new term here, it's much smaller than the previous one. Here, not that much smaller. So we have some work to do. We have a big gap to overcome. But at the very least, this is the first promising sign we've had that we can go between these two things. And we can talk about the normality of pi. And we can do this for more than just pi. There is, of course, another famous formula for example, natural logarithm of 2. So this would allow us to talk about, say, the base 2 normality of natural logarithm of 2, and this would hopefully allow us to talk about the base 16 normality of pi, which, as it turns out, is equivalent to base 2 normality. But that's what we'll talk.
So does if we know that the particular number is normal in one base, does that give us any information, like generally? I don't know. Let me rephrase the question. You said that if a number is normal in one base, that usually means that it's normal in all bases.
Yes, if you pick a number at random, almost certainly it's going to be normal to every base.
But I mean, but it's not.
That's not a guarantee that it's if it's normal to one base, that it's normal to a bunch of others. What you do know is that basically, if you are normal to a given base, you are also normal to any given integer power of that base. So being normal base 2 is equivalent to being normal base 4, and 16, and 32, and so on and so forth. And in fact, that's a really easy way, that's a very quick one to show. Okay, so say you have a base 2 expansion that looks like this. How do you get the base 4 expansion? Turns out, pretty easy. So there's this very natural way of going back and forth between the base 2 expansion and the base 4 expansion, and for roughly the same thing. So you can guess that if you're, for example, normal base 2, then all of the 2-digit strings should appear with the same frequency, which should imply that, for the most part, all the 1-digit strings here should appear with the same frequency. It's a tiny bit more complicated than that, but it has a rough idea of why it should work. There you go. Now, however, if you're talking about, say, base 2 and base 3 normality, then in fact, we know that there's lots of numbers base 2 which are not normal base 3. So one other wacky example I can toss out on the board real quick. So I've talked a lot about proving something is normal. What if you want to go the other way? What if you want to show that a number is not normal? In particular, what if you want to show a number is not normal to lots and lots and lots of bases? Because this is problematic. Going back and forth between base 2 and base 3 is the sort of thing that has mathematicians tearing their hair out, because it's not fun. So course, you could be rather simplistic, and you could just toss an rational number out and say, well, okay, it's eventually periodic, so therefore it's not going to be normal to any base you like. But if you ask the same question about irrational numbers, that's no longer quite so obvious. For example, the number I tossed out before that had way too many zeros base 10, I have no idea what happens to that number base 3. It could be normal base 3 for all I know. So it's actually a really challenging problem to get something that is not normal to a whole bunch of bases at once. And there's an example. For those of you who haven't seen it, this is product notation in the same way that a big sigma is sum notation. This is an irrational number. It is transcendental. It is not normal to any integer base. And basically the way that the proof of this thing works is that the construction here is such that in any base you like, eventually you're going to hit a string of, so say if you're looking at base 10, eventually you hit a massive string of 9s. That's so long that it doesn't matter what happened before it, you're just seeing way too many 9s. And it just destroys that limit that you're trying to show converges to a nice thing. And basically it does this in every base simultaneously. It's a really wacky thing. Now, of course, I have been trying to be careful about this and talk about, for example, integer bases throughout this entire talk. Well, we could talk about non-integer bases and say, does it make sense to talk about normality there? Yes, it does. Are there proofs of numbers which are normal to crazy non-integer bases? Yes, there are. They're, in general, not nearly as pretty as Champernoun's example, unfortunately. But, of course, that gets into the fact that basically any non-integer base is not very pretty to work with in the first place. Talk about pulling their hair out. That's it's awful. But that's most of what I wanted to say. So, any questions?
You talked about the rational method. Can that be expanded to any base so long as C is co-prime to the base?
Yes. Basically, if you replace 10 there by base B, then the resulting number will be normal base B.
Okay.
And there's several other different variants of that particular way. So I had C to the n times 10 to the C to the n. There's other things you could do. For example, C to the n times 10 to the C to the D to the n. I think something like that. Where D is just any integer you like. That one also works. Yes?
Is the density of the normal numbers in the transcendentals the same as it is in the irrational not transcendentals?
Okay, it depends entirely what you mean by that. And there's lots of ways to answer that question, and unfortunately I don't know most of them.
Okay.
I will say that I know there's a guy at the University of North Texas named Bill Nance who has looked at kind of questions along those lines of if you ask more complicated questions of density, how dense are normal numbers, and depending on which way you choose to do that, sometimes the answer is, well, they're not very.
Mm-hmm.
But it's not something I am particularly familiar with.
For the transcendental numbers, like if you, I mean, for all the numbers like E, I take it that there's every indication that they are normal.
E's actually a funny case. E appears to be normal for base 10, for example, but I can give you a fairly basic system in which we know E is not normal.
Okay.
Of course, this requires jumping out of the whole base 10, base pi, base whatevers into a slightly different way of writing down numbers, namely continued fractions. But there's a very simple continued fraction classical formula is due to Euler. And for continued fractions, there is a notion of being normal, and this fails it spectacularly. On the other hand, pi, for continued fractions, we have no idea.
You said that there are lots of cases of numbers that are normal base 2 but not normal base 3.
Yes.
Is there like a fun example that you would like to share with us today?
No, we don't know of any explicit examples, actually.
So we know that there's lots of them.
Yes.
Okay, I'm totally into it.
This is, again, the great problem of normal numbers. We know they're everywhere. You asked me to give you some, and I have to restrict myself to a very fine set of answers. And it's even worse in that case where if you ask me, okay, I want something that's normal for this base but not normal for this other base, provided those two bases, for example, aren't, say, 2 and 4, then the answer is, well, I know there's uncountably many, but after that, I don't have a clue. That is actually a question I would like to answer, but I don't at this point know an answer.
So are there any numbers normal in base 10 that do look random in their decimal expansion? I mean, that just sort
That
of
looks
intuitively.
much more intuitively random than these. That we know.
Right, that we know.
I'd probably say no to that. I don't really know of anything that truly looks random, just from the get-go. Of course, this again brings up the question of what is random, what is structured. I have a point here I wanted to bring up. Oh yes. So actually, as far as a notion of randomness goes, normality is a really neat one. So, for example, if I were to, again, construct a number by rolling a die an infinite number of times, then I would expect it to have a lot more properties than just that every string appears with the expected frequency. For example, I'd expect the variance between the expected number and the number I've actually got to occasionally be fairly large. And this is, for example, not true with Chamberlain's number. And this is a condition now known as strong normality. We don't know of any strong normal numbers at all. Yeah, it's kind of, there we go.
So it seems like a lot of these normal numbers have been specifically constructed to give examples of normal numbers, like
Yes.
Chamberlain's constant. Are there numbers like pi or e that have been in use for a long time, but then someone came along later and proved that they were normal, like they weren't specifically constructed to be normal?
The best I have seen so far, I believe there was a paper that someone has written recently where they attempted to show that, for example, square root of 2 is what is known as simply normal. That is where all the one-digit strings appear to the right frequency. However, I've seen a couple of people claim this over the years and be wrong. So I'm not certain how much to trust this latest one, but it's just a case of I haven't actually read the paper yet.
Okay. Also on a slightly different note, you discussed how the primes are usually considered to be not very strongly distributed.
Yeah, so the number of primes up to x is given as x over ln x. So
Right.
in general, we think of this as being very, very sparse.
So
But as
if
it turns
you-
out, it's dense enough for that property.
Right, so if you find a set of numbers that's denser than that, and then concatenate those, can that be proven to be normal?
That's denser than the primes?
Yes.
Oh yeah, sure, that's immediately true.
Okay.
But you can even do things that are less dense. So for example,
Right.
we don't know if this is true or not yet, but if there are an infinite number of twin primes, you concatenate those, you would get a normal number.
Okay, so if a set of numbers is concatenated and you know that there's a set of numbers that's less dense that's normal, then you also know that that set is normal.
Yes.
Okay.
If you're using that method of proof, yes.
Right.
Are there any more questions? All right, well, we are out of questions.
Okay.
Do you have any closing remarks?
Not that I can think of.
Okay. All right, well, everybody please help me in thanking Dr. Vandehey.
Okay, now I have one